Today we're going to talk about the motion of stars and planets across the sky. We talked about the basics of this in the Seasonal Skies lecture if you're an online student, or in the planetarium if you're a campus student. But we're going to do a little more in-depth with this lecture. We're primarily focusing on how constellations work, how stars are named, and the brightness of stars, which is referred to as a star's magnitude. Humans and our ancestors have watched the skies for millions of years. Surprisingly, people who lived hundreds of years ago actually knew a lot more about the night sky than most people today. Think about it. If I asked you to list as many constellations as you could think of, how many would you come up with? Some people might get the 12 well-known zodiac constellations, but not much else. Many people wouldn't even be able to come up with all of those. So why do we know the sky so much less well now? Well, what do you ordinarily do at night? Sit outside and watch the stars? Or sit inside and watch Netflix and play with your phone? There wasn't much to do before the invention of electric lights, so many more people spent time watching and learning about the patterns in the night sky. The same constellations appear at the same time each year, and planets follow a predictable pattern. To start learning the night sky, you have to go outside and find north. This is important because the North Star Polaris is the one star that does not appear to move in our sky. The stars aren't really moving around us, but they appear to move because of Earth's rotation. Earth's axis points almost directly to Polaris, and as Earth rotates on its axis, Polaris remains fixed while the other stars circle around it. So first, how do you find north? It's easy if you have a compass, as it points north, and most phones have a compass function in them now. Otherwise, find a couple of main roads you know. In Pensacola, Interstate 110, not 10, but 110, runs north and south. Highway 98 by the beach runs east and west. The sun appears to rise in the east and set in the west. At sunset, face the setting sun and make a 90-degree clockwise turn, and you've found north. To find Polaris in Pensacola, you'll look not directly up, but 30 degrees up from the northern horizon. Don't get up and north confused. If we were standing on the North Pole, the North Star would be directly overhead. But since Earth is tilted and Pensacola is at 30 degrees north latitude, we see Polaris 30 degrees up from the horizon. But you don't need a protractor outside to find 30 degrees up. If you make a fist and hold it away from you as far as you can, the width of your fist is about 10 degrees. So if you go 3 fists up from the horizon and look toward the north, you should see Polaris. An easier way to find Polaris is if you can spot the Big Dipper asterism. The two stars that form the front of the bucket point a straight line to Polaris. Remember, though, as the time of year changes, the orientation of the Big Dipper will change. So you won't always be pointing down and to the left. This is what you would see if you went outside in May. The Big Dipper's two pointer stars point down and to the left toward Polaris. But if I rotate my screen around 90 degrees, this is what we would see 6 months later in November, with the pointer stars pointing up and to the right. Only Polaris remains stationary in the sky. It's in the same location all night long and all year round. If you were to take a long exposure picture or take a video of the sky and watch it on fast forward, this is what you would see. Polaris is the dot in the middle, and the other stars make streaks called star trails as they appear to travel around Polaris. Since Earth turns from west to east, the sky seems to move from east to west. So if you want to look at something you know is in the western sky, you'd better look right at sunset before it disappears from view. Once you've found north, you need to know what to look for. It will depend what time of year it is. You will need a sky map, and here you see a picture of one. Can you see the Big Dipper pointing slightly up and to the right like we looked at just a couple of slides ago? This map is probably for November. Another way that you can tell is the constellation Orion is also visible, and he's only visible in the evenings during the winter months. If you wanted to see the constellation Hercules during this time, you'd be out of luck, as he's not up at that time of year. Now, so far, I've mentioned a few constellation names, but let's talk about where these names come from. Most of these star patterns we see in the sky maps were drawn by people long ago after their gods, animals, and heroes. Some of the pictures you see make some sense, others not so much. Here you see two constellation drawings, Scorpius the Scorpion and Sagittarius the Archer. The Scorpion makes sense to me. I see his head, his long body, and his curved stinger. The dots representing the stars match up pretty well with the drawing. Sagittarius, on the other hand, doesn't make a lot of sense to me. The dots that make up the teapot-shaped asterism and the rest of the stars surrounding it don't look a lot like someone doing archery to me. But there are alternative ways to connect the dots. If you're in my lab class, you should have already downloaded the Stellarium software. If you came to the planetarium show, at least you've seen the software. Even if you aren't in the lab, it's a free download you might want to consider installing on your computer while you're enrolled in this class. The default view of Sagittarius looks like this. And again, this doesn't look like an archer to me, but you can change the way the stick figures are drawn. Now look at an alternative view of Sagittarius. Doesn't he look a lot more like an archer now? Remember, a constellation is really just an area of space, so you can hook together the stars in an area any way you like. Some definitely make more sense than others. As I mentioned in the Seasonal Skies video, the zodiac constellations you find in horoscopes are 12 constellations that the sun seems to pass through. From the perspective of Earth in this photo, the sun is in Leo, meaning that from the Earth, it looks like the sun lies within the borders of the constellation Leo. Later in the year, the sun would be in another constellation as Earth moved along its orbit around the sun. As I also mentioned in the Seasonal Skies lecture, one problem with horoscopes is there really aren't 12 zodiac constellations. There are actually 13. One constellation called Ophiuchus is ignored and doesn't appear in this diagram, though it should, right here next to where this arrow is pointing. There are lots of other problems with horoscopes and astrology, but we'll get into that in your next assignment. If you were asked to plot the position of the sun or any of the planets on a sky map every day, what you would find is that they all follow the same path. This path is called the ecliptic, and it's pictured as this slightly wavy white line. and all the zodiac constellations fall along this curve. Note how Ophiuchus here does cross the ecliptic. The planets follow the same path because they all orbit in the same plane as the Earth around the Sun. The line of the ecliptic looks wavy, but planets don't actually bob up and down as they orbit. The reason why the line looks curved is that the planets orbit in three-dimensional space, but we're trying to picture it in a flat, two-dimensional picture. It's the same reason why you sometimes see maps of the Earth that look like this. Trying to make spherical Earth lie flat is going to yield some strange curved edges. Trying to plot orbits on a flat piece of paper have the same issue. There are 88 constellations, 39 of them in the Northern Hemisphere. Remember, the constellations are not the stars or the dot-to-dot drawings. Constellations are just an area of the sky. The whole area of the continental United States is divided into 48 states. The whole sky is divided into 88 constellations. These circled stars are the brightest stars in the constellation of Orion. His stick figure is often drawn like this. It's important to remember, though, that all the stars in this area are also part of Orion. So this star, and this one, and these up here are also part of Orion as well, not just the ones we normally see connected in the stick figure diagrams. Here is another sky map that shows several constellations. Notice that some of them don't show stick figures, while others connect only some, but not all of the stars. Alternate stick figures you see result from people connecting more or fewer stars in different ways. Notice that in the Ursa Major constellation, the only part of the stick figure is the Big Dipper asterism. But there are many more stars within the boundary. Ursa Major is the Big Bear, and it's often drawn more fully like this, to include his head, body, and legs. Also notice that some stars have names, like Regulus, while others have numbers or Greek letters, like this guy over here, named the Greek letter pi. So within a constellation, there are a bunch of stars that are all in the same general direction. However, it's important to remember that just because two stars look near to each other, they may not be. For example, my house is off Highway 98. My parents also live right off Highway 98. However, if you were driving from Pensacola to my house, it would take you only about a half an hour to get to my house. You'd have to drive an hour and a half farther to get to my parents' house. Same direction, but very different distances. The stars in the picture Orion that we looked at 2 slides ago all look about the same distance away, but some are many times further away than others. The 2 stars at the bottom of the stick figure look relatively close together, but this one is about 100 light years away, and the other one is over twice as distant. Asterisms are what people are often talking about when they use the word constellations. Asterisms are created when you make stick figures by connecting stars in the sky. The Big Dipper pictured here is an easy-to-spot asterism that takes up only part of the Ursa Major constellation. Similarly, the Teapot asterism takes up only a small portion of the constellation Sagittarius. The concept of the celestial sphere sometimes seems a little complex. The idea came from the fact that way back in history, people thought that Earth was the center of the universe. They pictured space almost like a bunch of Russian nesting dolls, where you have a series of larger and larger spheres surrounding the Earth on which the planets and stars were attached. Look carefully at this picture. Look first at the tilt of the Earth. It's tilted way too far over, but it's showing the perspective of someone living in Pensacola. Look at the little person in the center. He's standing like he is on top of the Earth, but he isn't at the North Pole. The North Pole is where the red axis is coming out and pointing to the right. It's pointing about 30 degrees north of the horizon because we live at 30 degrees north. You can see that the zenith is the point straight up above his head. And notice that this is not the same as north. Then notice the big circle around Earth. This is the celestial sphere, and ancient people assumed all the stars were attached to this sphere. And as the sphere rotated, the stars in the sky moved. Now, if this picture or this section of chapter 2 don't make a lot of sense to you, don't stress out about that too much because space isn't actually organized in this way. There isn't a giant sphere surrounding the Earth with all the stars stuck to it. But even though there is no celestial sphere out there surrounding the Earth, it does give us a pretty good image of what's going on. It helps us understand the geometry and perspective of what we're seeing. Why we can see some areas of the sky only during some parts of the year, and why what we see changes over the course of the year. This is a model of the celestial sphere that you can buy online. I have a similar one in my classroom on main campus. Earth is in the center, and the other little yellow ball represents the sun as it appears to go around the Earth. The big clear sphere is where we see images of the stars. Depending on where on Earth you are and where the sun is with respect to the Earth, you can determine which area of the sky you will be able to see at night. This is how ancient people thought space was set up. In astronomy, we often talk about how many degrees, seconds, and minutes things are apart from one another. Think about a circle as being 360 degrees around. Each of those 1 degrees are broken into 60 minutes. Then each minute is broken into 60 seconds, just like time. We won't use these measurements a lot in this class, but it is where the unit parsec I mentioned in the cosmic zoom lecture comes from. A star that is a parsec away seems to shift by 1 second of parallax, a very small fraction of a degree. We'll talk more about this later when we get into the math of how distant stars are. Earlier in this video, I mentioned that the North Star Polaris appears to hang 30 degrees above the horizon to us here in Pensacola because Pensacola sits on 30 degrees north latitude. However, depending on where you are on the planet, that will vary. If you were in Boston or Detroit, much farther north, Polaris would be at 42 degrees up from the horizon, much higher in the sky since they are at 40 degrees north latitude. If you were at the North Pole, Polaris would be directly overhead at your zenith. If you were on the equator, which is 0 degrees latitude, you'd barely be able to see Polaris on the horizon. If you were anywhere south of the equator, Polaris would not be visible at all. That also means that stars other than the circumpolar stars will spend different amounts of time visible in the sky based on their location. This person is in Pensacola at 30 degrees north latitude. The stars rising and setting along the celestial equator, you can think of these as the stars that hang above the equator, are visible for a long period of time. A star rising in the east at sunset would be visible for 12 full hours until it set at sunrise. However, a star farther south would follow a much shorter path and may be visible for only a few hours. Polaris and other nearby stars are visible all night for people who live in the northern hemisphere. Polaris is the only one that seems not to move at all. Nearby stars seem to trace a circle as they move around Polaris. Some stars in circumpolar constellations may dip slightly below the horizon for short periods of time, but they would return quickly as the Earth continues to rotate. These are a few of the circumpolar constellations. Perseus, Cassiopeia, Cepheus, and Ursa Major are listed. Draco and Camelopardalis are two more not pictured here. These constellations, or at least parts of them, are visible all year round. If you've ever looked closely at a star map, you may have noticed that some stars have very strange names. This is true for a variety of reasons. First, many stars were named thousands of years ago by Arab astronomers. They were the best astronomers at that time. One star in Leo is called Algeba. You may notice how similar that word is to the word algebra. Both those names come from Arabic. Many other stars are named in Greek, and we'll see more of those later. So if the only language you speak is English, a lot of star names will appear strange to you. Some stars have names that describe the star itself, or where they are in a particular constellation. For example, Deneb is the star in the tail of Cygnus the Swan. Antares is a bright red-orange star that looks a lot like the planet Mars. Antares literally means rival of or anti-Mars. Mars is the Roman god of war, and Ares was his Greek counterpart. The star is named this way because if you're not careful, it's easy to mistake the star Antares for the planet Mars. I won't expect you to memorize these names and what they mean, but I do want you to recognize the fact that some stars are named in this way. Many stars are simply given a Greek letter as their name. The Greek alphabet's first four letters are alpha, beta, gamma, and delta. So the brightest star in a particular constellation is often given the name alpha. The second brightest is beta, and so on until you run out of Greek letters. These are the most common names you see on star charts today. In addition to the Greek letter, the star has to get another designation to tell you which constellation it's from. This is because every constellation has an alpha and a beta and a gamma star and so on. So the Greek letter is like the star's first name, and the possessive form of the constellation is like the star's last name. In this example, the brightest star in the constellation of Centaurus is Alpha Centauri, a star very nearby the Sun. Similarly, the second brightest star in the constellation of Gemini would be Beta Geminorum. The first name rates the brightness, the last name identifies which constellation it is found in. So let's look back at the map that we looked at earlier. Here are several stars that each carry the Alpha designation. Each of these stars are the brightest one in their respective constellations. This one is Alpha Ursa Majoris, while this one is Alpha Leonis. You do not need to memorize all the Greek letters, but you should know the first few letters in order. Alpha, beta, gamma, and delta. as these stars are the brightest ones in each constellation. Here is another example showing two images of the constellation Orion. Alpha Orionis and Beta Orionis are the two brightest stars. They also have the more commonly used names Betelgeuse and Rigel. In the photo, you may notice that Rigel appears brighter even though it carries the name Beta. But it's possible that it was less bright compared to the Alpha star at the time when it was named. In addition to names, another important thing you need to know about a star is its magnitude. Magnitude is a way to compare the brightness of stars. Early astronomers called the brightest stars first magnitude stars. This is often abbreviated as Mag 1. Slightly dimmer stars were called second magnitude stars, or Mag 2 stars. Stars even dimmer than that were called third magnitude, and so on. The larger the magnitude number, the dimmer the star. A dorky way to help you remember that is the bigger the magnitude number, the bigger the telescope you'll need to see it. Stars with a higher magnitude than 6 cannot be seen without a telescope. There are actually two different magnitude scales. One measuring apparent magnitude, meaning how bright it looks to us. The other measuring absolute magnitude, meaning how bright something actually is. The difference may not be obvious at first, but imagine you're looking at a lit 100-watt bare light bulb from just a few inches away. It's very bright. But if you go 30 feet away, even though it's still putting out 100 watts, it looks much dimmer. If you were a mile away, you might not even be able to see it at all, even though it's still putting out light. It's important to know if you're talking about magnitude, which one you're referring to, apparent or absolute magnitude. We're only talking about apparent magnitude now, how bright things appear, but we'll get into absolute magnitude later in the course. Over the years, the magnitude definitions have gotten more specific. Though they're still measuring relatively the same thing, we have a mathematical way to represent the differences in brightness. Magnitude 1 stars are 100 times brighter than magnitude 6 stars. Magnitude 6 stars are the faintest ones we can see with the naked eye, and each magnitude differs from the next by about 2.5 times. So let's look at a couple of examples. Let's say star A is a magnitude 3 and star B is a magnitude 4. This means that they are one magnitude step apart. That means star A is about 2.5 times brighter than star B. Remember, the star with the bigger number is actually the dimmer star. The smaller the magnitude, the brighter the star. In another example, let's say one star is magnitude 1 and the other is magnitude 3. From 1 to 3, that's 2 steps down in magnitude. So 2.512 times 2.512, 2 steps, is 6.310 times. One star is over 6 times brighter than the other. Don't get too bogged down in the numbers. We'll work with numbers more later, but for now, you should know that each magnitude star is about 2.5 times different in magnitude from the next number. Based on this mathematical refinement, the bright star Sirius in the constellation Canis Major is actually a -1. That means it's very bright. The planet Venus is even brighter. The full moon, and obviously the sun, are much brighter still, thus have numbers even farther to the negative side of the scale. The Hubble Space Telescope is capable of seeing stars as dim as magnitude 28. That's much too faint for telescopes on Earth's surface. You don't need to memorize any of these numbers, but this chart is a handy way of quickly comparing the numbers and objects that are easy to find in the sky. Finally, these are a couple of equations that you will come across during the chapter readings. It's actually only one equation. It's just rewritten depending on what you're trying to solve for. FA over FB is the ratio of flux, or the brightness of the two stars. The rest of the equation is 2.512 raised to an exponent of the differences of magnitude between the stars. Don't worry about the math with this equation right now, but I do want to emphasize this 2.5 number again. Remember, this is the number of times brighter one star looks than the next magnitude down. You'll need to know this number.